R1. Similarly, R2 tends to SHR R2, which means that you are going to apply a logical shift right on the register R2. This is the way of representing a logical shift right and logical shift left. Now we'll see one example how to implement this shift micro operation. Let us consider a register R1 which contains the data 1101. The register R1 is of size 4 bits and the range is from 0 to 3. The 0th bit contains 1, first bit contains 0, second bit contains 1 and the third bit contains 1. We already know that whenever you are representing the data, this registered data, the RHS part, the extreme right data is known as LSB bit, least significant bit, and whichever is present at the extreme left, this is known as MSB bit, means most significant bit. Now this is your register. If you want to perform a logical shift left on R1, see how the data will be shifted. You always need to move the bits of the register to the left side. One bit should be shifted to the left side. See how the data is going to be changed. SHL on R1. So this will be moved to one position to the left side. This again moves to one position to the left side, and this one will move to one position to the left side. Whenever the third bit, this bit comes in this place, in this MSB position, you can discard the original MSB value. Whatever the original value which is present in the MSB position, that can be discarded. When you see this register after applying the shift to left operation, your MSB bit is filled and this bit is also filled and this bit is also filled, but this LSB position is empty. So as per the definition of logical shift, what is the logical shift definition? See here. The logical shift is the one that transfers a 0 through the serial input. So a 0 will be transferred here. The 0 will be transferred at the LSB position as per the definition, and you can discard MSB in case of a logical shift. So what is a logical shift? Each bit of the register should be shifted or moved one place to the left side. Each bit should be moved one place to the left side. When you are performing this, you can discard the MSB position and a serial input of 0 can be transferred at the LSB position. Now coming to logical shift right, it is represented with SHR. In case of left, we are moving the bits of the register to the left side. In case of logical shift right, you will move the bits of the register towards the right side. One bit is moved to the right side. Consider the same register R1 which contains 1101. Whenever you are applying the logical shift right operation, what happened? The bits will be come here, this will come here, and this will come to this 0 will come to the LSB position. When you are moving to the right side, you will discard the LSB position. Why? Because the LSB position is filled with this 0th bit. The LSB position is filled with the value 0 which is present in the first position. Again here, nothing is there in the MSB position. This MSB position is empty when you perform a right shift operation. So what you can fill at the MSB position? According to the definition of shift micro operation, a serial input of 0 can be transferred at the MSB position. This is your logical shift operation. Mainly logical shift means moving the bits of the register to the left side and moving the bits of the register to the right side one by one at a time. In case of logical shift, MSB bit is discarded, LSB bit is filled with 0. Whereas in case of logical shift right, your LSB is discarded and MSB filled with a serial input of 0. That is the first type. What is the second type of shift microoperation? It is circular shift. When you see in logical shift, what happens? Some of the data is lost. If it is a logical shift left, MSB data you are discarding means the MSB data is lost. If it is a logical shift right, what happened? LSB data is lost because you are discarding the data at LSB position. So, to avoid that, you are moving to the circular shift. What happens in circular shift is the bits of the register are moved either to the left side or to the right side from one end of the register to the other end, and in this case no new information is added. At the same time, content of the register is, it will not be lost. Content is not content, there is no loss of information and no new information is added. It is also known as a rotate micro operation. Circular shift is also known as rotate micro operation. We'll see why we are calling this as a rotate micro operation. Same as logical shift, your circular shift can also be implemented to the left side or to the right side. If it is CIL R1, it means that R1 bits are shifted to the left side circularly. If it is R2, CIR R2 means the content of the register R2 is moved to the right side, one bit. One bit is moved to the right side circularly. That is important, circularly. Consider one example for circular shift left. This is the register R1 which is of range 0 to 7 bits. That means size of the register is of 8 bits from 0 to 7. And this is the content of your register 000, 10, 111. Right? When you want to apply a circular shift left, simply apply the logical shift left mark. You already know how to apply the logical shift, right? One bit is moved to the left side by one position. So, the bits will be moved like this in case of logical shift. But the difference is, if it is a logical one, you will simply discard this MSB position and you will include a serial input of 0 at the LSB position, right? But here in case of circular shift left, what happens is, once the remaining all the bits are moved to the left side, the MSB bit is placed at the LSB bit, so that you did not add any new information and this original data is not lost. It does not lost. That is what a circular shift left means. In case of circular shift right, what happened? See, this is your register of size 8 bits from 0 to 7. Simply apply the logical shift right. You know how to perform a logical shift right. Just move the bits of the register. Just move the bits of the register one by one to the right side. But in case of logical one, what you will do? This LSB position is discarded and a serial input of 0 is transferred at the MSB position. Just in case of circular shift, what happens? Simple change is the LSB position, whatever is there at the LSB position, that will be copied into your MSB position, so that no new information is added, nothing is lost. That is your circular shift right. Why we are calling this as a rotate micro operation? Because the bits are rotated from one end to the other end. These are the bits of your register, right? So, you are moving, when you are moving towards the right side or towards the left side, you are moving the bits from one end to the other end. That is, LSB is moved to MSB in case of right shift, and in case of left shift, what happens? MSB is moved to LSB. That is the reason you are calling this circular micro operation as a rotate micro operation. And the last one is arithmetic shift. Three categories are logical shift, circular shift, and the last one is arithmetic shift. Let us see what is this arithmetic shift micro operation. So, arithmetic shift micro operations are mainly used for signed data to perform a shift operation on a signed data. Whatever we have discussed, the logical and circular, they can be implemented on a unsigned data. On an unsigned data. That means you will not specify the sign of the data. Whenever you are specifying the sign of the data like plus and minus on the register's data, if you want to perform a shift micro operation, you must use arithmetic shift micro operation. Right? You already know if it is a decimal number, for representation of a positive number, you will simply use a plus symbol. For a negative number, you will use a minus symbol. But here it is your binary system. That means everything is in the form of plus and minus, in the form of zeros and ones. You will not use plus as you will not use minus symbol. Right? Then how you will know the sign of the number? How you will know? Always the sign of the number is known using the MSB bit. The sign of a number is always known using the MSB bit for assigned data. Right? So this is your MSB bit, right? The last one, the extreme left bit is your MSB bit, right? If the value of MSB is 1, it represents a negative number. If the value of MSB is 0, it represents a positive number, right? So, when you want to perform a shift micro operation, you will not consider, when you want to perform arithmetic shift operation on a signed data, you should not consider this MSB bit as a original value. What is the original content? You must consider from here, from R minus n to R0. For example, I'll show you one example. Let us suppose this is your signed data. Assume that R1 is having a signed data. If it is unsigned data, how you will calculate the corresponding decimal number for this? 2 power 0 into 1 plus 2 power 1 into 0 plus 2 power 2 into 1 plus 2 power 3 into 1. Whatever is the result, that will be the corresponding decimal number. But here, if it is a signed number, you will not include this value. This MSB position is used only to represent the sign, right? If it is 1, it represents a minus value. What is the value? 2 power 0 into 1 plus 2 power 1 into 0 plus 2 power 2 into 0, that is 4 plus 1, which is equal to 5. So, the value of this register is minus 5 because the symbol is, the MSB value is 1. So, to perform a shift operation on the signed data, then you will use arithmetic shift right. Now, we will see how to perform this. Again, this shift, arithmetic shift can be done either to the left side or to the right side. Let us consider this is the registered data. This is your registered data. What is this value? 0. This MSB value is 0, which means that it is a positive value. The value is positive. How to perform arithmetic shift left? Arithmetic shift left is simply equivalent to your logical shift left. You know how to perform a logical shift. The bits of the register are transferred to the left side one by one. The bits of the register are transferred to the left side one by one, and you will discard this position. A serial input of 0 is transferred at the LSB position. Right? This is your logical shift. Arithmetic shift left is also equivalent to logical shift left. One thing to be remembered in case of arithmetic shift left is, whenever you perform an arithmetic shift left on a register data, then the result is a multiplication of The result is a multiplication of 2. For example, the value of this is something like 5. The value of this, I am just giving one example. I'm just telling, I'm not telling that the value of this corresponding binary decimal value is 5. Just assume that if the decimal value is 5, whenever you perform a arithmetic left shift, whatever the result you will get, it is a multiple of 2. 5 into 2, this should be equivalent to 10. When you convert this into decimal value, you should get a 10 value. That is what happens in arithmetic shift left. Here I have included that point. An arithmetic shift left multiplies a signed number by 2, right? So if you are performing an arithmetic shift left on a number with the value as 6, then you will get the result as 12. Now, one more thing to be remembered here in shift left is, here the MSB bit is 0. That means what? It represents a positive value. Whenever any value is multiplied or divided, the sign won't be changed. If you multiply a 6 with 2, you will get a positive 12 only. If you are multiplying a minus 6 with 2, you always get a minus 12. That means if the value is positive, the result is also positive. If you are multiplying with 2, the result should also be positive. If this value is negative, you should also get a negative value, because whatever the result you are getting is a multiplication of 2. But what happens is, here this 0 is a positive number. Now, whenever you apply a logical shift left, what happens? Whatever is there at the 6th position, that will come to your LSB position. Whatever is there here, that comes here. Here you have a 0, so 0 will be transferred in the LSB position. So if this MSB position value is 0, it represents a positive. This is a positive. When you apply a logical shift also, you got a positive value. So in this example, you don't have any problem. But assume that if the bit value here is 1, the bit value here it is 1, but the MSB is 0, that means it is a positive value. Now, whenever you apply this left shift, what happens? This 1 will come here. This 1 will come here. Now, what is there in the MSB position? 1. Whenever the MSB is 1, this represents a negative value. But when you are multiplying any number with 2 or dividing any number with 2, the sign should not be changed. But here you are having a positive value. After applying the left shift, if you are getting a negative value, it represents an overflow. The sign difference represents an overflow. What is an overflow? When this overflow will occur, all that we'll see in the next unit. As of now, you need to remember that in case of arithmetic shift left, whenever a sign difference comes, it represents an overflow, and that will come only in the arithmetic left shift micro operation. Why I am not explaining about the overflow here is, you may get confused. That is the reason I'll explain the overflow concept clearly in the next unit. Right? Now we'll move on to arithmetic shift right. This is also similar to your logical shift right only. This is your register data. Simply move the content of the register towards the right side, one bit at a time. Bit by bit transfer towards the right side. When you are transferring towards the right side, if it is a logical shift, what happens? You will simply discard your LSB position and a serial input of 0 will be transferred at the MSB position. But what happens in arithmetic shift is, here this 1 represents, it is a negative number, and the same symbol will be copied at the MSB position. If you will have 0 here, you will copy the 0 here. If you have 1 here, you will simply copy 1 here. Why? Because always arithmetic shift right divides the number by 2. arithmetic shift right divides the number by 2. If it is a left shift, it multiplies the number by 2. I already told you that whenever you are multiplying or dividing any number, the sign will not be changed. So, whenever you are applying a logical shift right, assume that the value of this is 16. The corresponding decimal value for this is 16. When you perform an arithmetic right shift, what happened? You will get a value as 8, 16 by 2. The result will be a division by 2. If it is minus 16 by 2, it will give minus 8. So, the same value, the same sign will be copied in the MSB position. This is about arithmetic shift micro operation. So, shift micro operations are mainly decategorized into three: logical shift, arithmetic shift, and circular shift. Now we'll see. So when it comes to arithmetic shift, what is to be remembered? In case of arithmetic shift operation, if it is a right, it divides the number by 2. If it is a left shift, it multiplies the number by 2. In case of left shift, a sign difference will occur. If the sign difference has come, it represents an overflow. But that sign difference won't come in arithmetic shift right operation. These are the 3 points to be remembered in arithmetic shift micro operation. Now we'll see the hardware implementation of this shift micro operation. Before that, let us see, we have a register A which contains the bits from A0 to A3. We have a register A which is of size 4 bits. A0, A2, A3 are the 4 bits of your register. So consider a 2 by 1 multiplexer. 2 by 1 multiplexer. Now, on this register, if you are performing a shift right operation, what will happen? The bits will be moved towards the right side like this. And at the LSB position, a serial input will be included. That serial input can be anything. In case of logical shift, this serial input will be 0. In case of circular shift, this serial input will be equivalent to A3. In case of arithmetic shift, that will be in case of that will be A0. That will be the same MSB value. In the same way, if you are shifting towards the left side, then the bits will be moved to the left side like this. A1 will come here. Sorry, this is from A1. So A1, A2, A3, and a serial input will be included at the LSB position. Serial input will be included at LSB position. So here the serial input can be 0 in case of logical shift. It is A0 in case of circular shift, and it will be the MSB value in case of what? This arithmetic shift. Now see the what we call hardware implementation. Here the size of the register is 4. So we are going to consider 4 multiplexers. And the size of the multiplexer is a 2 by 1, because you can either perform a left shift or you can perform right shift. Only 2 options, 2 possibilities were there. That is the reason you are considering a 2 by 1 multiplexer. The input can be a shift right or a shift left. Only one will be performed at a time. So from 2 inputs, right and left, you will get 1 output, right? So if the size of the register is n, then you must have n multiplexers. Now, before we discuss about this hardware implementation, just see the functional table. So whenever the bits are like this, when you are applying a shift right operation, the bits will be IR, A0, A1, A2. IR, A0, A1, A2. When you apply a shift right operation. Now, in case of multiplexer, 2 input, as the size is 2 by 1, so it should have 2 inputs, 0 and 1. Whenever the number of inputs are 2, how many select lines you should have? You should have a single selection line. One selection line you should have. as the selection line is 1. So how many values you can have for selection line? Either 0 or 1. If the selection line is 0, it represents a right shift. If the selection line is 1, it represents a left shift. If it is 1, represents left. If it is 0, it represents right. Now when you see this truth table, whenever S is 0, it represents a right shift operation. And in case of right shift operation, the bits will be like this. The register bits are what? A0, A1, A2, A3 will become IR, A0, A1, A2. IR, A0, A1, A2. Similarly, whenever the value of S is equal to 1, it represents what? It represents a left shift micro operation. And whenever you perform a left shift, what are the register bits? A1, A2, A3 and IL. A1, A2, A3 and IL. So from the first multiplexer, you will get the output as H0 because what is the multiplexer? From multiple input lines, it will select only one output line. These are the multiple input line. It will always give a single output line. So the single output from the first multiplexer is H0. From this it is H1, H2 and H3. Now let us see what are the input lines to be connected to the multiplexer. One is the selection line. So that can be either 0 or 1. Now to get this output H0, what should be the input lines? What are the input lines? To get output as H0, from where you are getting this H0 as output? From the first multiplexer. So what are the two inputs to be given to the first multiplexer? IR, that is your serial input, and A1, that is the bit of the register, second bit of your register A1. So one input is IR, which is your serial input. Second input is connected to what? Second input. Here we have a dot. This input is connected. Second input is connected to A1. In the same way, you are getting H1 as output from this multiplexer. So what are the two input lines to be connected? Two input lines to be connected to this multiplexer are A0 and A2. So one input line is your A0 and the next input line is your A2. These are the two input line. Similarly, H2 is the output coming from this multiplexer. So the two input lines to be given are A1, A3. One input line is your A1. Here you have a dot, means this is the input connected to this multiplexer A1 and the next input is A3. When it comes to H3, it is the output coming from this multiplexer, the last one. The inputs provided should be A2 and a serial input IL. So one input should be connected to your A2 and the other input should be connected to your serial input, which is your IL. Is it clear? So this is your shift micro operation, the categories as well as the hardware implementation of shift micro operation. Is it clear for everyone? If yes, I'll move on to the next topic. With that, the second part of your first unit will be completed. I'm planning to complete that also in the today's session only. You please let me know whether this shift micro operation is clear or not. If you are having any doubts, please let me know. Shall I move on to the next topic? Okay. The next topic is arithmetic logic shift unit. Till now, we have discussed arithmetic micro operation and their hardware implementation. Logic micro operation and how to implement that using hardware component. What are the hardware components required to implement logic micro operation we have seen. Similarly, just now we have seen how to implement a shift micro operation and its hardware implementation also we have seen. Instead of having a separate circuit for every micro operation, here you can have a combined circuit which will implement all the micro operations. A combined circuit which implements arithmetic micro operation, logic micro operations, as well as shift micro operation, that is known as arithmetic logic shift unit, which implements all the operations. Now we'll see how how the hardware implementation of this arithmetic logic circuit unit. So your arithmetic logic shift unit, it requires one stage of arithmetic unit, one stage of the logical unit. One stage of arithmetic unit is required, one stage of logic unit. What this arithmetic unit will do? This arithmetic circuit or unit will perform all the arithmetic micro operations like add, subtract, increment, transfer, decrement, and so on. Similarly, this is your logic unit. This circuit will perform logic micro operations like AND, OR, XOR, NOT, and so on. Right? So, one stage of arithmetic is required, one unit of logic is required. This complete thing is known as one stage. Right? Now, you should know what are the inputs to be provided for these two circuits. What are the inputs to be provided? When you see this arithmetic circuit, so I hope you remember this arithmetic circuit which we have discussed in the previous classes. So, using this circuit, you can implement your arithmetic micro operations, right? So, what are the inputs to be provided? Inputs to be provided for this arithmetic circuit are the register bits. Consider you have two registers A and B. The register bits are to be provided as input, right? Next, what are the others? One, carry input A0 and B0. The register bit should be provided as an input along with the registered input as it implements arithmetic micro operations. In case of addition operation, you require a carry value, right? So the carry input Cin should also be given as a third input to the arithmetic circuit. So in this circuit, in this implementation also, this arithmetic circuit is also given with three inputs, that is Ci, which is your carry input, and Ai, that is the first bit of register A, and Bi, the bit of the register B. These are the two bits of the register. Similarly, the logic circuit, you just see here. So your logic circuit should also be given with how many inputs? It should be given with two inputs A1, Ai and Bi. That is the registered bits Ai, Bi should also be given as inputs to the logic circuit. And you are implementing all these arithmetic circuits as well as the logic circuits using the multiplexer. So these multiplexers should also be provided with the selection lines. Two selection lines. That means here I have considered a register of size 4 bits. That is the reason I am considering here a 4x1 multiplexer. Size of the multiplexer is 4x1. So it should be provided with the two selection lines S0 and S1. So these two selection lines should be given as input to both the arithmetic unit as well as the logic unit. Now what this arithmetic unit will do? This arithmetic unit is responsible to perform all the arithmetic micro operation, but all the operations cannot be implemented at a time. Only one can be selected. What is the use of this multiplexer? So by using this selection line, any one input can be selected. One input can be selected. That means as this arithmetic circuit is implementing addition, subtraction, increment, decrement, transfer, so on. All are implemented by this arithmetic unit, but any one can be selected as your output from this. So this di can be either add or subtract or increment or any arithmetic micro operation. In the same way, your logic circuit is also provided with the inputs AI and BI. That is the bits of the register, but only one input will come. That means either an AND operation or any one operation will come as output from this logic circuit, right? Now, here I am going to consider one more multiplexer of size 4 by 1. Why? Because the size of the register here it is 4 by 1. So, here arithmetic circuits and logic circuits you have considered as 4 by 1. But why I am considering a 4 by 1 multiplexer here also? Why? Because what are the inputs you are getting? So, this is arithmetic operation 1. Logic operation is 2, second input. Next, shift micro operations are also there, right? In shift micro operation, you can again having two types. That is right shift, that is your third input, and left shift, which is your fourth input. So, it is provided with 4 input. That is the reason we are having 4 inputs. That is the reason you are considering a multiplexer of size 4 by 1. You already know that if the size of the multiplexer is 4 by 1, how many selection lines you should have? You should have 2 selection lines. Here I have represented them as S2 and S3. This complete thing is one stage of your arithmetic logic shift to unit. That means it is for A1 and B1. Next, for A2 and B2, the same type of circuit you should have one more. For A3 and B3, you should have one more. For A2 and B2, you should have one more. If the size of the register is 4-bit, these type of circuits or stages, how many you should have? You should have 4 stages of this type. 4 stages of this type. This is one stage for 1 bit of your register. Now we'll see what are the selection lines to be provided to get different micro operations. What are the selection lines to be provided? Using this arithmetic logic shift unit, you can get 8 arithmetic micro operation, 4 logic micro operation, 2 shift micro operation. We'll see what are those micro operations are. Right? This is the table. What are the inputs you are providing, ma? Here, you just go through this. What are the inputs you are providing to this? You are providing 2 selection lines. Based on these 2 selection lines, any one input from 0 to 3. That is either DI or EI or SHR or SHL will be selected. But to get this DI, here your DI is the output of one more multiplexer, right? DI is the output of one more multiplexer. Similarly, EI is also output of one more multiplexer. So, to get this DI, what are the inputs to be provided? Inputs to be provided are AI and BI and one carry input. Which input is selected is again based on the values of your selection lines, right? From this circuit as well as from this circuit, from this logic circuit also, based on the values of these selection lines S0 and S1, one micro operation will be selected. So when you see this function table, so based on the combination of these selection lines, one micro operation will be selected. See, S3, S2, S1, S0 and one more is Cn. This Cn is used whenever you want to get arithmetic micro operation. But this Cn is not required for logic micro operation because carry is not required for logic micro operation, and for shift micro operations also carry input is not required. So I told you that this circuit is giving you 8 arithmetic micro operation. So till this you have arithmetic micro operation and 4 logic micro operation. So these are your 4 logic micro operation and 2 shift micro operation. When you see this Cin value, this Cin carry value is required only for arithmetic. So for remaining logic and micro operations, you don't require carry value. So I just put a cross mark here. So whenever the values are like this, the corresponding function or the corresponding micro operation will be performed. So if the values of all the selection lines is 0, then a transfer micro operation is performed. If the selection values are like this, then increment operation is performed, addition, add with carry, subtract and decrement, so on. So these are the arithmetic micro operations performed. Now when it comes to the logic micro operations, what are the inputs to be provided for logic micro operations? So you require only these four selection. Based on these four selection values, based on the selection values of S1 and S0, one EI will come, and based on the values of S3 and S2, one final output will come, right? So you don't require CI for logic circuit. So for logic circuit, you don't require CI. So these are the different combinations. The different combinations are 1, 2, 3, 4 to get 4 different logic micro operation like AND, OR, XOR and NOT. Complement means simply NOT operation. Similarly, when you see this hardware circuit, to perform this shift micro operation, what is required? So to this multiplexer, you are given second input for implementing right shift, third input is given for implementing the left shift operation, right? Either left shift or right shift, any one can be performed at a time. Which one is to be performed is always decided by the selection value. So what are the selection values given for this multiplexer? These two, that is S3 and S2. So to implement shift micro operation, you don't require the values of S1 and S0. Don't require the values of S1 and S0. So when you see this functional table, S1, S0 are empty. Similarly, Cn is not required for logic micro operation, and it is not at all required for shift micro operations also. So only two inputs required. Or what are the two combinations of S3 and S2? If it is 1, 0, a right shift is performed. If it is 1, 1, a left shift is performed. Right? This is about your arithmetic logic shift unit. So with this, the second part of your first unit is completed, ma. There is one more part which is instruction formats. With the third part, your first unit will be completed. Any doubts? Please let me know if you are having any doubts. I'll give you 5 minutes for doubts clarification. If you don't have any doubts, then I'll start the quiz. Any doubts? Please post it in the chat box, ma, if you are having any doubts. Otherwise, I'll start the quiz. Or else you just go through these PPTs. I'll share these PPTs. Go through them once. And if you are having, after reading those, also if you are getting any doubts, you can post it in the CR group. I'll clarify. Or you can personally message to me. I'll clarify your doubts. So shall we start the quiz? You are saying that no doubts. You are not having any doubts. So shall I start the quiz? Okay. Okay, ma, I'm going to start the quiz. Thank you.